Hello guys, hope you're doing well. My name is Mahmoud Jazari and welcome to the new chapter of Power System. If you guys remember in the previous chapter, I had a little bit of background why we're using the power system. I talked about the transmission planning job, and after that, how we are going to implement everything we learned in the university related to the power system in our some kind of day-to-day life as the transmission plan. So at this point, I would like to, again, step a little bit back and talk about the whole power system, start from the very basic ideas of the power system itself, different kind of definition, and so on and so forth. So in order to reach that part, again, I'm going to have this introductory part related to the whole power system itself. Again, we had this very, very good session, I can say, related to the whole power system concept for the last part. You can just always watch it and try to some kind of really understand what's going on from the perspective of the university students to the perspective of the transmission planning job. So at this point, let's talk about it without any further ado. So as I just told you, the reason that we are talking about the kind of power system is that we are going to deal with the largest interconnection machine on Earth, which is going to be the power grid. So in the power grid itself, we had different kind of parts. We had the generation, we had the transmission part, we had the distribution part, and so on and so forth, and everything that happened in between. So at this kind of sessions about related to the power system, I would like to talk about all of those concepts, and it means that we should have some kind of steps. Step from the from the beginning, which is related to the cluster 1, that I would like to talk about the foundation of the power systems. It means understanding the language and some kind of basic physics of the grid. Then we would like to move to the cluster number 2, which is about the components. So at this point, we are going to talk about the modeling the physical reality of transformers and lines, which plays a crucial role in the whole system itself. And finally, we are going to have an analysis. We are going to talk about the per unit module, running the power flow, analyzing any kind of fault that we do have in the system. Again, let's have one step back to see what do we mean when we are talking about the power plant. What do we mean by talking about the power chain? If you guys remember, the last session I talked about the very important part, which is going to be the generation. It means that at the very beginning of the point, at the very beginning point of this chain of commands, we do have the generation. We do have the coal, we do have the wind turbine, renewable energies, distributed energy resources, and so on and so forth. So we are going to consider them as a generation. So then we do have the transmission plant, because if you guys remember, it's not feasible to move that voltage we produce, maybe it could be a couple of kilovolt through the transmission planning, because as you guys remember, if you move the voltage or if you move your electricity through the wires because of the high currents that you have for them, if you consider the constant amount of power, which I'm going to talk about in the next slides, so you are going to have lots of current. Having lots of currents means that you are going to have lots of losses. So lots of losses means that the amount of power that you produce, that if you consider as a P of gen, you know it would be equals to the P of loss plus P of, for example, receive. So if this P of loss is going to be so high, the amount of power that we get out of this generation part is not going to be that much. That's why we have to find a way in order to reduce the amount of loss. How we're going to use that? We are going to use the transformers. So transformers are going to help us in order to what? In order to reduce the amount of power loss. On the other hand, when we are talking about the distribution level, it means that we have to move from the transmission that we have the high transformer. It means that they're going to convert the low voltage to high voltage. Again, we have to reach from the high voltage to low voltage, because at the end of the day, we would like to make sure that our customers, they're going to have this some kind of feasible amount of voltage, not going to be that so much high voltage, like 100, 200 kilovolt. It's going to kill everything that you have, all of your devices, right? And finally, we do have the loads itself. It means that from the distribution level to load, don't worry about it. We are going to talk about all of these pieces of the puzzle. The very first thing that we have to talk is about the translating the physical reality into engineering language. As you guys know, in the physical reality, we do have our system in 3 phases, phase A, B, and C, which you guys probably know about that. I will talk about it in the next slides, but we do have it in our physical reality. But when we're talking about our system, it's going to be a little bit challenging to model all of that, especially when we're talking about our big grid, our big, some kind of massive lines that are going to be interconnected to each other. In order to make everything a little bit easier or simple for the calculation, we do have the abstraction. In abstraction mode, instead of 3 lines, we're only going to show them with 1 line, while we know that this 1 line still is going to replicate those 3 phases. But we assume that those 3 phases are going to be a balance that we, again, I will talk about it, what does it mean by balance and not balanced system. And we do have our system itself. It means that we do have the generator. We're going to show it like this. Then we do have the transformer. As you guys remember, we are going to increase the amount of voltage in order to reduce the amount of current. Then we do have this bus, or it could be the transmission line. And then we do have the step down transformer. And finally, we do have the loads itself. So again, these 2 things are going to be the exact same thing, but at some points we do have the physical reality, and another point we do have some kind of abstraction. So again, let's look at our some kind of abstraction mode. That's something we call as SLD. That is something we call it as single line diagram. So SLD is very, very common these days, especially when you're talking about the transmission planning, or we're talking about the distribution planning, or any kind of power engineers, or any some kind of job that is actually related to electricity and power. They know about the SLD. The very first thing that we do have is about the generation. The generation could be anything. It could be coal, it could be wind, it could be renewable energies, it could be battery, it could be anything, right? So at this point, we do have the level of voltage. This level of voltage could be from a couple of kilovolts to maybe around 20 to 30 kilovolts. But as you can see, it's not that much. So when we are talking about the voltage, when we are talking about the generation, we are talking about what? We are talking about P equals V times I, right? So the voltage and times current. As you guys remember, I told you that the amount of power that we can produce is something constant. Yes, I know we can change some variables, some kind of features in order to get more power, yet this power is something constant. So it means that if I do have the low amount of voltage, which 10 kilovolts and 20 kilovolts we do consider as a low amount of voltage in comparison to the megawatts of power that we are producing, we are going to have high amount of current. This is the balancing. This is the trade-off, right? Having high amounts of current means that in the line between the generation part to the distribution part, or just to the load part, we are going to have the high amount of current, and at that point we do have RI squared. Why we are talking about that? Because transmission line or any kind of cable line wire, they do have the resistance. If you do have the resistance, which is something constant, but you do have the high amount of current, you do have the higher amount of power loss, because power loss has a relationship with the power 2 of the current itself. And at the end of the day, you're going to have lots and lots of heat. That's why we use the step-up transformer. Step-up transformer is going to increase the voltage, means that my V is going to be higher while the current is going to be less. So at that point, my power loss is not going to be that much. And then when you do have the step-up transformer, you do have the transmission line. Probably you just see that, you just saw that one. And when you're moving towards cities, especially in the highways, you saw those big and massive, some kind of pillars that they are carrying the very big cables, and those big cables are considering as a transmission lines. And then we do have the substation. So in the substation, when you do have all of those power that's going to be transmitted through the generation part, distribution part, or at least a local part that is going to be close to the load or to your home, we do have the part that we call as a step-down transformer. Step-down transformer means that we do have the high amount of voltage, imagine that 138 kV, and then obviously you have to reduce it down. So this reduced down step-down transformer is going to be your substation. And at the end of the day, you do have another kind of transformers that is going to be in your alley, it's going to be in your street, but those guys are going to convert that amount of voltage. That distribution part can reduce it down to way down to something around 120 volt per each phase in order to use it for the day-to-day life. When we are talking about the SLD, it's very important to know the symbols. So the very first important symbol is something that we call as bus or bus bar. What is bus bar? Bus is the place that all of your components are going to be connected to that point. Imagine that when I do have some kind of this components, yet we don't know what is that. This part, which is going to be called something we call as a feeder, or feeder is going to be load, and then we do have another component. All of these components, they should be connected to a point. The point of interconnection, or the point of connection of all of these components, is something that we call as bus. Then we do have the circuit breaker. What is the circuit breaker? That we see it like this, like a square, means that obviously you're all very familiar with the matter of fuse. The fuse is something that is going to be in the way of the electricity in order to protect your system. Because if you don't have it, and if something happens because of the fault, because of any kind of issue, and the current spikes, it's going to damage your device. In order to protect that, you do have the fuse. Imagine that you're dealing with kilovolts or hundreds of kilovolts of power. Of voltage. So obviously, in order to handle those amount of problems or have the protection for your devices, especially transformers, because those things are some kind of fragile, are not going to be that kind of strong thing, especially when you're dealing with huge amounts of error, and also those things cost a lot. So you're going to protect them. So protection is something that we call as a breaker. So breaker is somehow will act like the fuse itself. And finally, we do have the transformer. The transformer symbol is going to be like that. Two interconnected circle like this. Either we do have the step up or step down transformer. So again, why do you have the inefficiency of low voltage? As you guys remember, I told you that when we are talking about something like the voltage ladder, it means that we do have 500 kilovolts with 30 kilovolts, 69, this one and this one means that we do have this massive amount of kilovolts as a transmission part, and we do have this 120 volt as a voltage in your house. But as you guys remember, I told you the amount of generation that we do have because of our power plants is going to be constant. So P is equals to V times I. And if I keep that voltage, something around that, my current is going to be so high. And this current of high is going to cause a power loss. This power loss is going to be high. This is something that I really like. That's why I'm trying to convert this amount of voltage to something higher in order to reduce the amount of current. And this amount of current, which is going to be this amount of current due to the fact of transmission part, which is going to be 150 to 765 kV, is going to reduce the amount of current, and we do have the less amount of loss. Obviously, I'm not going to keep it that way. That is only for transmission part. For the distribution part, I'm going to keep it like that. And then for some kind of other transformers inside your house, I'm going to reduce it down as much as possible. So probably you heard about the AC. This means that the alternative currents, but the DC are the direct currents. So they do have some kind of advantage and disadvantage. But the reason that right now we're talking about the AC is that it is easier to be converted. They convert from one voltage level to another level. That's why you all heard a story about some kind of this fighting between people that who support AC and the DC. DC was for Edison, and after that AC was for one of his students. So we found out that the AC would be way better because we can use the transformer because of the electromagnetic systems that we are going to touch it in the future. But just have it in your mind, the AC at this point would be cheap. It's going to be some kind of the passive, and it's going to be highly reliable. On the other hand, it doesn't necessarily mean that DC is bad, because obviously DC is the voltage that you need for your devices. You need still the converters to convert the AC to DC. So DC is good, especially when you're talking about the transmitting their power through their very some kind of long distances. This is something that we call as a high voltage DC or HVDC. And another thing is that while we're saying that AC is good, it's still going to cause some losses that we don't like. That's why DC system at some points is also going to be helpful. Again, it's a matter of trade-off between the AC and DC. It doesn't necessarily mean that AC is bad or DC is good. So you should compare those sessions that you need. So when you're talking about the AC, obviously we're talking about the three phases. As you guys remember, in the physical board, we do have three phases of cable or three cables. We call it as A, B, C, or maybe you just call it as another one. But these things in an ideal world, are going to be the balanced three-phase physics. It means that you do have three different kind of vectors that obviously the vector has a magnitude, has an angle, and these three vectors and the magnitude wise are going to be the same. The only difference between them is going to be the phase angle between those guys. Imagine that I do have my first vector, it has this amount of magnitude and the zero angle. Then I do have my second part, which has 120, and another one which is going to be negative 120. But at the end of the day, if you add these guys, which we consider their balance together, you're going to have the big zero itself. So this is the thing. This is the analogy behind those three phase. And when we are talking about the balance system, it means that if you add them up, it's going to be zero. Obviously, your system is not going to be balanced all the time. So we do have some kind of problem because of that. We'll talk about them in the future itself. Another thing that you have to know is the difference between the phase voltage and line voltage. What is the phase voltage? Phase voltage is going to be the voltage between your phase and ground itself. Ground plays a crucial role in some kind of the power system, so it is very important. It means that if you measure the voltage from one line or some kind of one phase to ground, it's going to give you a value. For instance, the value that we all know is 120 volts. Another important number is the difference between the lines or between the phases that we call as V line to line or phase to phase, and its relationship between the phase itself is that V line is √3 times V phase itself. Not only about that, the difference between those two guys, it means that the V line and V phase is going to be the 30 degrees of difference. We're going to touch these values and touch all of these concepts in detail in the future. Again, I'm going to give you a very big picture of what we are going to talk about. So this is the difference between the line and between the phase itself. Still, we are considering that the phase are going to be like this, like that, and like that one. And we call this connection as a Y connection. Well, Y or literally just Y or Y connection because it's just like normal Y. And if you were to consider this guy as a ground, the ground would be over here. In a balanced world, the adding of this one, this guy, and this guy is going to give you a 0. So it means that if everything is okay, it doesn't matter if you do have this ground or not, everything is still going to be fine. But we are going to consider the ground because obviously we are not living in an ideal world. Another thing that we have to know is about the grid Achilles heel. It means that the cascading failures. What does that mean? If you guys remember, for the previous chapter, I was talking about the contingencies. So what was the contingency? It means that our system is not going to work on normal operation all the time. In the normal operation, you do have line 1, line 2, line 3, everything is normal, everything is feasible. But imagine that you do have a fault and one of those lines is going to be tripped. So what would happen? The power still would like to move through your lines, but instead of just being dissipated or being divided equally between all those three, you have line 1 and line 3. Line 2 is gone. So the power inside each of these lines are going to be way higher. It means that they're going to accumulate the amount of power. At some points, they can handle it for maybe a couple of seconds, a couple of minutes, but at another point, they cannot handle it. And it means that they do have a capacity called as thermal capacity. So if thermal capacity is getting higher, you do have your breakers as your protection. So breakers are going to sense that and they're going to what? They're going to disconnect everything. But the disconnection doesn't necessarily mean that you're going to only protect your device. The disconnection means that you're going to put some pressure on the system because at the end of the day, the amount of generation and the amount of consumption plus loss should be the same. But imagine something happened and this balance between them are going to be imbalanced. So it means that you're going to have the problem. But not only your device is going to be disconnected, other devices that are connecting to your device, it means that, as you guys remember, the grid is interconnected, some kind of the interconnected wires, interconnected some kind of cables, interactive neuroscience. So if we do have pressure on one side, it means that other side also going to feel the pressure. If that one pressure is down, another some kind of all of the pressure of the whole system is going to be transferred to another one. But when the next one feels that pressure, that system is also going to feel that one and its protection is going to be activated. So imagine this kind of problems, which something we call as cascading failures, are going to be side by side, and something we do have it as the massive blackouts. It means that your system is down, nothing works, and after that you have to find a problem, solve it, then restart and move back everything to the normal itself. So when we are talking about this kind of aspects, obviously we cannot accept this amount of the problem, or this we aren't going to accept this huge amount of cost of time and money just because based on our guesses, right? As you guys remember, I told you that that's one of the jobs of the transmission planner people is that to simulate this problem. How we can simulate this problem? By simulating the actual grid in the system. Either different kind of software, we call it as PSCAD and PSSE, and by putting them inside that one and putting your system under pressure, under intentional pressure, it means that we are going to give the system some faults. We're going to see that what would happen. Imagine that you do have your system is going to be bus A to D, and then we are going to have some trips. While all of them are connected, we are going to put the trip. At this point, almost everything is normal. But as you can see, the amount of thermal capacity between these two sections are going to be higher and higher. At some points, they can handle 210% or 233% of their normal capacity. But if anything happens and these numbers are going to be way higher, the protection devices are going to get activated, and you're still going to have those cascading blackouts, or you're still going to have your failure. That's why in the simulation software, we are going to model the system, see that if anything happens to them, and if not, system is good. If happens, we're going to find the problem itself. So again, the scenario over here is that the primary transmission line just tripped offline because of any fault over here, and the challenge is that which of the remaining phase will immediately absorb this kind of displaced power. So the risk is that identify which specific line at this point, for example, the 92% will exceed its thermal limit. So it exceeds the thermal limit, we have to stop it. Rather than that, we are going to damage your cable, we are going to damage any component that is connected to that cable. So let's talk about the generation, because normally when you're talking about the generation, the very first thing that you have in your mind is about the coal, is about the traditional way of some kind of other power plants that we used to have. Everything was simple. It means that it was one way, where it was only from the generation part to your house, and everything was simple. But at this point, when we are moving towards the clean air, when you're moving towards the new technologies, we do have this kind of two-way of power generation. It means that instead of just normal coil, we do have the wind turbine, we do have the solar system, and those things are going to be connected to your load. But on another hand, you don't only have the solar, some kind of solar panels in the solar farm. Obviously, you're also going to have it at your house, at your some kind of the company or whatever is that. This is something that we call as DER, or distributed energy resources. These distributed energy resources are not massive, yet they are going to be connected to the grid. It has all of those crazy electronics in itself. I'm not going to talk about that, but it means that not only your system is going to only consume this power, but it's also going to inject this power to the grid itself. So we do have the two-way connection. You all can imagine that how massive those calculations would be, how complicated everything would get. So it means that we do have the transition from the traditional part to the modern part, which happens because of the renewable energies, and this everything is going to cause a bidirectional flow. And obviously, we do have some kind of spike in demand because of the electrical vehicle, because of the number of the population that moving towards the city are going to get higher and higher, and we do have so many of those challenges. So at this point, at this some kind of session, we talked about the core principle of the grid. We talked about the chain of command between the generator, transformer, and so we do have the transmission, another transformer, and distribution, and finally the load. We talked about the language, the difference between the phase and the line itself, and obviously we talked about the vulnerability of your system, that if anything happened to the grid itself, well, what are some kind of the consequences? And we are not going to accept this luxury of getting failure, and obviously you can't accept all of those time and cost by just install everything by making them, install them, and test them in the real life. Before that, we are going to test them in what? We're going to test them in the software, the PSK and PSSC. We are going to touch them in the future. Don't worry about that. But that was a very, very big picture of the power system. Obviously, when you go inside that one, you have to know other concepts. Active power, reactive power, apparent power. This is something that we are going to see them a lot. So a lot of questions in order to completely make sure that we understand everything. But obviously, you don't have to constrain, you don't have to limit yourself to this part, to this some kind of videos. After understanding every part, you have to go through the textbook, you have to go to a different website, maybe solve a lot of questions in order to completely feel comfortable with any kind of problem or any kind of solution that you have during your university days, or maybe some kind of your day-to-day work job. My name is Mahmoud Kiosari. Thanks for watching me. Have a super great day, night, whatever. See you.